Hello, good morning, everyone. So welcome back for today's first session. So Professor Mohanty will be talking about gravitational waves, and please proceed. Thanks.
So I'm going to talk about stochastic gravitational waves and how they are observed in pulsar timing arrays. So you already heard a very nice comprehensive talk by Ghulam about this, but I'll give you in this talk some basic theory behind these observations. So the basic theory is that we are here and we pick any PTA collaboration picks a ring of pulsars and the average distance is about 1 kiloparsec. And the gravitational waves which are passing through in all directions, so they have a lambda. So basically 10 years is 3 nanohertz. That's 3 parsec. So one third nanohertz frequency is what this 10 years of observation would be sensitive to this frequency and that wavelength. So the wavelengths observed are much smaller than the distance to the pulsar. Okay. So what is observed is that you pick a pulsar, let's say pulsar A, and you have a model waveform that's the mean time of arrival. So this is the time of arrival of peak. And this distance is t, and t is like a millisecond. So you have a millisecond period, and this is a theory. So this is the average. So this goes periodically. So this is the theory. And then you have the observations where you have one peak and the second peak maybe shifted a little bit and so on. So this shift in the peak is called, this is delta t, and this is also a time series. At different times you'll have different shifts in the arrival time of the pulsar. This I am giving. And so what is taken is that for each pulsar, you define this quantity Za, which is this delta t divided by Ta. Okay, and this is a function of time. Then what we do is we take the time average of this cross correlation between two different pulsars. Time average, and this time average is over the 10 years or whatever is observation period of the thing. So this is the cross correlation between two different pulsars. And I'll tell you what is the shape of this cross correlation which is observed, and then I'll try to derive it, that why it should be like that. I mean, what is expected and what is observed. So this is written in frequency space. There is the integral over frequency. And this is, let me call So this depends upon two factors. One is this power spectrum. So I'll tell you in detail what is this. This is the power spectrum of the gravitational wave, that what is the amplitude of each wave at different frequency. So I'll explain that later. And this is a function of this angle between the two pulsars. So this is theta AB. So this is pulsar A and this is pulsar B. Okay. And what is predicted, and this was done by Hellings Downs in 1983, is the following. So this is theta AB goes from 0, 90, 180 degree, and it looks something like this. Something like that. So the dip is near 90, something like 80 degrees. And you want to, so this is what I'll derive, that what is the shape of this curve, why it should be like that. Okay. If you have a stochastic, that randomly gravitational waves are passing in all directions of different frequencies, why you should see a shape like this. But if you want to visualize it, you can think of the following, that let's take a ring of pulsars, and you have seen when you have a cross polarization, this Gopakumar said he will explain in more detail the actual visualizations of these pulsar, the polarizations. But I have written the two polarizations, H plus and H cross. So H plus is when it oscillates like that. So in time, it goes from like that to like that. So ring becomes ellipse in one shape, and in between it's a circle and so on. So this is in time. So what happens here is that the space-time, so if you look at two pulsars in the same direction, okay, the space-time is squeezed in the same, so either they are both squeezed or they are both elongated. Okay, I'll show that mathematically next. On the other hand, if you look at two pulsars which are 90 degree apart, okay, the space-time is squeezed in one direction but elongated in the other direction. So then this Z is positive in one case, negative in another case. So at 90 it becomes negative, okay, and then again when it's 180 degree, okay, the correlation becomes positive, because when this is squeezed, the next antipodal point is also squeezed. So it again becomes positive. Y-axis, thank you, C theta AB. So this is the Hellings down correlation. And of course, you don't have one wave which is passing, but roughly the stochastic average reproduces this scenario. So all the other directions cancel, and this is the, and it's of course not a perfect correlation and anti-correlation. They don't anti-correlate exactly at 90, and they don't have perfect correlation at 180, which is to do with the stochastic nature. It's not just one wave passing like that. Yeah, so the source could be anything. So all you need is early universe, reheating, massive, supermassive black holes, any source. What it is, if it produces nanohertz frequency, okay, and I think an amplitude of something like 10 to the minus 17, Gulam may correct me, the strain of 10 to the minus 17, then you will see it in PTAs. 15. Okay. Yeah. So H is 10 to the power minus 15, which is much larger than what you observe in LIGO, which is less sensitive than LIGO, but you have a stochastic. And frequency is nanohertz. So in this range, if you have produced gravitational wave, so this was plus polarization, but the cross polarization is just a 45-degree rotation of the same thing. Okay, and when you are talking about this cross correlation, that when you have a rotation, it's the same story. You can convince yourself that the cross correlations remain the same. The mutual angle remains the same. So if they are opposite, they are squeezed, and if they are in the same direction, they will be elongated. Oh, sorry, either 90-degree, the correlation will be negative, and if they are 0 or 180-degree apart, then there will be a positive correlation. So if it's a stochastic, if there is a isotropic GW background, then this correlation is just a function of this theta AB, the angle between the two pulsars. It doesn't depend upon any overall general direction. Okay, so there is no preferred axis. It's just the only correlation thing that matters is the two. So we will see how that comes. Okay, so this is the thing, and some NANO-Grav, etc. give you these observations, and then you can work out whether these observations are, how statistically significant these observations are according to the theory or not, whether fit this curve or not. Okay. So then how does this curve come about? So I'll start with, so what we are going to do is basically, the picture is that we have Earth here, pulsar A here, and this is at a direction NA, and here we have some gravitational waves passing, and they are in the direction N with some frequency F. So, okay. Now, this is the general how you write the metric, delta Ij plus Hij xt. Okay. And so we are talking about for null propagation. So we are looking at this light which is propagating from the pulsar to this place. So this was Na, but this is the direction of the propagation. So for the photon propagation, ds is 0. So what we are trying to find out is the difference in the arrival time, because perturbed by this Hij. Normally the time of arrival would be just the distance, but there is a perturbation here. So from one pulse to the next pulse, in between, if the average of this Hij changes, then you will have a difference in the pulse. Okay. Shift in the arrival time. Okay. Yeah. No, I have no intuitive way, but yeah, mathematics. Also, you can ask why it is shifted from 90 degree to 80 degree. And yeah, yeah. Yeah, thank you. That was nice. So just remember that it is not one wave which is passing through all the pulsars which we are measuring. It's a different waves, but when we take the cross correlation, it will be, I'll explain how that picks up a correlation between the two, although you have random waves passing through all. Okay, I'll explain that later. So this was just an intuitive picture. This is the dominant wave which matters in the averaging. Okay, but of course it's not exactly correlation and anti-correlation. Okay, so then ds is 0, which means that the time of flight of the light beam is dt square is dx square, which I will write as 1 plus na. Okay, I have taken out dx square, where this ni is basically, so na, the vector, is simply the direction of the, which I'll also call, sorry, the direction from Earth. So I will take the Earth to be 0. This is the pulsar, and x is equal to 0 here at the observation. And the ij component, I will, oh, what did I do here? Sorry. So I have taken the component of a and I and j according to the hij here. Now, of course, if you actually want to have to put this in the final formula, it won't make sense because you don't know what are the directions of hij. But you'll see in the averaging, the components won't matter. It's the overall Na which will come in. So this is just an intermediate step where I've taken the components along the hij projections of the wave which is perturbing this signal. Okay. Okay, so this is basically, this tells you that dt is dx and now let's put this is a function of t and x, and we integrate both sides. Okay, and what we'll do is that t emission, t observation, dt, and here we will say that this dx is dt as c is 1, and that doesn't mean the actual path length is the same as the time. There is a perturbation here, but the measure is the same. So I'll replace this by dt, and this also will be from t emission to t observation of this whole thing, 1 plus. So t observation minus t emission, and the first one was dx, so that is the same. I'll keep that as the distance. The first term I keep at x, second time I'll write as t. So plus dt Now remember that this x is over here is not just any random point in space-time for this Hij. This is the path, the Hij on the path of the light beam. So the time and x are related. So this xa is a fixed number, but this x is a variable. So this x goes from 0 to xa, and we are looking at the Hij on this path. So basically that means that my x here is related to t, and that is t emission minus, plus d minus t na. So when t is equal to 0, basically, I mean from t emission to t observation, this x goes from there to there, xi to here. Okay. So now let's take a form of the gravitational wave. Just for this will be Aij cosine omega t minus kx. So this x is on the path length of this beam, which is integrated over, and k is just the direction of the graviton, which is an independent direction. This is not an a, okay, times the frequency. Okay, so I substitute x from there and write k as this. So basically I have Aij, which is a function of n, cos omega So substitute x, k from there and t from there, and omega multiplies everything. So there is one more bracket. Okay. All right. So what are we looking for now? What we have to do is substitute this waveform here and calculate the observation time, take the emission time other side. So what we need is the following. So we are looking at this. So let me call it the first pulse, the first signal and the second signal. So what we are looking at is delta t, the residual, which is t observation for 1 minus or 2 minus t observation for 1, the observed time of arrival, and subtract the model period. It should be t, you subtract that. Okay. So this is the thing we are looking for, and you can then convince yourself, or it's easy, I can show you, I'm sure I'll show you, that this basically delta t is, so this delta t is basically t times the, so basically we are looking at the arrival time, the emission time of the first this thing is 1, and the second peak is t emission plus t. Okay. And we want to compute this observation time from this formula for two different emission times, one at t and one at t plus capital T. Okay, and remember this t is very small compared to any of these time series. T is millisecond and your observation time is like 10 years. Then you can do a Taylor expansion of this. So I'll just write down that, and so this is T times T emission of this quantity, because the other one, these things will cancel if you subtract T. So you bring T emission to this side. Okay, so it's T emission plus D, and the next one will be T emission plus capital T plus D, and then you subtract T. So when you subtract the two observations, this part will go away, and you'll only get this one. Okay, so actually here I could have just done the integral, and I made him, yeah. So here in the T observation is equal to T emission plus D, plus I do this integral, and this integral will give me Aij. So I am doing this integral divided by 2 omega 1 plus Na dot n times cosine omega T emission plus D So what have I done? I've taken this waveform, inserted it here, and done the integral over, and this cosine should now become sine. This. And these are the two endpoints. I have evaluated it at the two endpoints, and this factor comes from the integral of T emission, this T. So there was this factor of, where did I, this, yeah. If you insert it here, I think I wrote it wrong, sorry. This is omega T times 1 plus that. Okay, sorry. Yes, I'll write that. So this is there, and here there is a Nij, and there was a factor of 2. So Ni, Nj, A. Okay. So basically this is the, so this is my observation time. Okay. And now I do the next step, take this observation time for a given emission time, that's the first peak. And then I take emission time at T emission plus an extra period T, and then subtract the two. Okay, and then subtract from that the capital T. So this part goes away. The other part is just the Fourier, the derivative of this whole thing. Okay, so the derivative of this will be basically, so I will not, I'll give you the answer now. So derivative of this would be this times T omega 1 plus n dot Na. And this was derivative with respect to delta T is equal to T times d by dt emission of this T observation as a function of T emission. Okay. So if I stick that here and take the derivative of with respect to T, I will have a omega, because T emission is multiplied by omega, right? So that omega cancels. So and I'm back to this cosine. Cosine of omega T emission plus D minus cosine of T So if you now interpret this, that if I write it as a general form for the Hij, basically this tells me that this, and so I'll keep it like that. So I call Za T to be delta T by T. So I take this down. This will be 1 upon 2, 1 plus n dot Na, the and Aij and this, I'll write it as a general Hij again, just to interpret what it is. This is T observation, emission plus D is just the observation time, and here the x is equal to 0, okay, minus Hij omega T emission Xa dot n. So basically what you do is, if you take this formula and write this Hij in terms of Aij times the cosine of this argument, you will see that, so this is x is equal to 0. So for this put x equal to 0, and for this put x is equal to Xa dot n, you will reproduce that, okay, using by that general relation cos omega t minus kx. So basically this tells you that this thing is sensitive to the gravitational wave at Earth and at the pulsar. And I think for the cross correlation, the Earth term doesn't matter because that is common to all the pulsars. Okay, so this is not relevant. So what matters is the gravitational wave at the pulsar. Okay, so this was a bit of tedious calculation, but there is no steps I have skipped. If you go back and put down things, you'll get this. Just follow the. Okay, now next is what is the cross correlation? Okay, so the cross correlation will turn out to be, okay, I will write. So what I do is, first I write my Tx as sum over polarizations in the frequency space df, okay, and over all angles, integrated over all angles of this h lambda f n. So this omega is 2 pi f now, the frequency, T minus Nx. So what I'll do is I'll substitute the Hij in that formula with this, and so it will become a function of this frequency distribution of this gravitational wave in the Fourier space, which depends upon the frequency and the direction of the propagation. Okay, so this is the amplitude of the gravitational wave in the Fourier space. And then I do the crucial thing, which is take the stochastic average, or so this is an assumption. This is lambda h star Fn lambda prime this is equal to the power spectrum SF. So this will, I'll just tell you what is the power spectrum, and this will be some function of f delta f minus f prime, delta function of n prime, 4 pi for normalization, and okay, so this is the crucial step. So what this tells you is that in that step, we had gravitational, if you have a cross correlation, we are taking the gravitational wave at pulsar A, and this one will be the gravitational wave at pulsar B in the frequency space. So what this step tells you is that unless you have the same frequency and the same polarization at the two pulsars, there is no correlation. Which means that there has to be a same one source which is supplying gravitational waves to both the pulsars. Okay. They are not out of phase like Golam said, but there should be a identical frequency and the polarization and the direction of propagation at both sides for the both pulsars for this to count as correlation. Otherwise, there is zero correlation. So this is the step. You put it there. That means apply that. If you substitute this h here, there will be two integrals over frequency, but that will go away with the f minus f prime. There will be two omega n's d omega, but one you can get rid of this delta function, and again there will be one sum over polarization. So finally, what you will get is the following. Okay, so the final answer is that ZA T. So we use the fact that the time average is the frequency average. This is half df02 S of f d omega n. This is upon 2 pi. So this is the GW n, not the pulsar n, times lambda plus and cross of some function which I'll just tell you what. And this function is basically FA lambda NAI So this is the function which we picked out from that formula. So that formula reduces to this in the frequency space, as you can see, using this average over the stochastic averages and reducing two frequencies and two angles to one. So in the end, there is just the integral over a frequency of the gravitational wave distribution, okay, and integral over all the angles of that gravitational wave, okay, and so you are left with this this is also A, not B. These ones, and you have to do the integral, okay, and I'll just give you quick this thing that how to calculate this. So you can take supposing you have a gravitational wave going in this direction, you can take an orthogonal triad. So this is U and this is V, okay, three orthogonal vectors, and you know how to write the orthogonal vector. So N is cos theta, sin theta cos phi, and theta sin phi cos theta, and similarly U will be, let's say, sin phi. These are unit vectors. So if you take this, these are mutually orthogonal vectors, okay, unit vectors, and they depend upon the direction of the graviton. So basically this, you take this U and V, this defines my Ij plus, which is, so this is my polarization for a gravitational wave in the n direction, and this is Ui. So this you can look it up in some basic text. So this is, let me write Ui Uj. Should be careful, Ui Uj. Ui Vj plus Vi Uj. Okay. So that is it. So what you now do is take these angles, okay, put this in this and do this angular integral. There is only one set of angles, which is the gravitational direction of the gravitational waves. Okay. So it's a tedious, tedious means it's a tedious calculation in the angular part, but nothing. So look it up. I won't do it now. Bruce Allen and Romano. 2208 04302. So this, look up the appendix of this angular integration is performed. So at the end of it, what do you get? So in the end, the final answer is that, let me erase this. Some C theta AB, which I just wrote, and then so this is the spectra, the frequency dependent part, and there is the angular dependent part, which I separate. Okay, and this angular dependent part is just that thing, which I just calculated, which is not just, which I just defined. Theta AB is basically So this is my Hellingsdown correlation function, where FA and FB are basically functions of two angles. One is these things are a function of FA is a function of NA and N, and FB is a function of NB and N, the direction of the pulsar and the direction of the gravitational waves. I put that in, integrate over the direction of pulsars. Okay. Then I am left with just the sum function, which is just the mutual direction of these two waves. So this answer, if you do this comes out to be so this theta AB will be XAB log XAB minus 1 by 6 1 by 3, and where XAB is just sine square theta AB by 2. And that is the Hellingsdown plot that I gave. So that leaves us with what exactly is SF. So let me just tell you what is SF. So as I said, it's a complicated answer. There is the overall simple way to understand the general shape is what I had shown in the pictures. But if you want to look at details, it's not very clear unless you work out the formula. Okay. Now, what is so to be able to predict from a model this correlation, okay, the fact this part doesn't change. This is to do with the spin-2 nature of the graviton. So if you have some other field like spin 1 or spin 0, you'll get a different correlation. So for a spin 1 field, this is just simply cos theta AB. Okay, if you have a spin 1 field which was doing this, oscillating, some spin 1 field is oscillating the pulsar, you will get a correlation of theta AB, which also sort of fits that observation on NANO-Grav. Now, you start with the formula. So all you have to do is supply that SF. And what that SF represents is the energy density of the gravitational, that stochastic background of gravitational waves. So I'll start with, Ashok wrote yesterday, the TIG of the gravity of gravitons, E mu of gravitons, okay, which you get from Einstein's equation, and you take the zeroth component, T00. This has a simple form, 32 pi g times Hij dot the time derivative of Hij. Okay. And then this Hij, if you write it in the frequency space as an integral over frequency and then use those 2 the stochastic averages. So this is an integral over f, that is an integral over f prime, but there is, when you take the stochastic average, there is a delta function of f and f prime, which will leave you just one integral over f. So all that will give you where this f, okay, is now related to this rho as follows. So rho will be in the frequency space you defined as d rho by df, d log f. And this is rho of GW. This is the rho of GW. And I think so this will be, if I take this formula, this, okay. First I have this rho of GW, then I define my omega of GW, which is rho divided by rho critical, and my critical density is, as depends upon the h naught square divided by 8 pi g by 3. So if I take that formula, okay, calculate this and calculate omega GW, my final answer, which is okay, so this is the relation basically between the SF that goes into that calculation and the density of the gravitational wave, which is, so if you have a model and you predict the density of the gravitational wave, and then as a function of frequency for at each frequency, then you can calculate SF, and then that will give you the Hellingsdown correlations. So I think that is all today. This was the basic. So you have actually 2 lectures on this PTA. So Gopakumar will tell you in full detail all this. I just wanted to give you the 0th order introduction to the subject, and then you can learn more about the details from him. Okay, thank you.
So, yeah, questions?
Yeah.
Yeah, it's a bit of naive question. I just couldn't get the last part where you omega of GW is rho by rho critical, where you are taking rho to be that rho of GW, that integration part, right?
Yeah, so basically you write this as df and multiply by a f, so that there is a f cube here. Yeah. This is d of log f. Take d by d log f on both sides and you will get this coefficient. Take d of d log f. Okay, so this is d of log f times f cube sf, right?
Right.
Then you take d by d log f, that defines my omega at the frequency space. So that will just the coefficient, and then I divide by the critical rho. So that's why you have a f cube sf here.
Okay.
Okay. So this is from the usual, the earlier one, df 2 pi f square is just the d cubed k. It's 4 pi k square dk.
Yeah, you're looking in the frequency space.
Yeah.
Other questions?
Yeah.
Hello. Yes. So I was wondering that imagine you have a stochastic gravitational wave by background, just you have done, but they are polarized. That means chiral. Okay. So does all the steps remain the same, or do you?
No. So what you do is the last step. Instead of taking the sum of the polarization, you take only the polarization that you have in the background. So you will get a different expression compared to that.
So then will it be able to distinguish between, like, from the Hellingsdown curve?
No, so you are no longer will get the Hellingsdown curve. Whatever is a new curve, you compare that with the observation.
Okay, and that will carry the information of how much the left-handed gradient.
You see, in that derivation, I wrote f lambda, and I summed over lambda. Instead of summing over lambda, keep one lambda and write the polarization in terms of this UV according to whatever is your polarization. Okay. So you will get a different expression there for that curve, and you compare with observations and see.
Yes.
So you have to do a lot of algebra there, but it's interesting. Yes.
So my question is that so observationally, what we see that those peaks, what you have drawn. So now, can you just summarize that? Given those observation, how do I reconstruct this stochastic gravitational waves?
The better person to answer is Golam because he actually does this.
Okay.
So
Okay.
I'll let him answer.
So my question is, what we are seeing those only those peaks that apart from the pulsar observations, that some frequencies, some signal is coming for a time interval. So given that observation, how do I reconstruct these HIJs? Because so
So in the time series, you actually explained this a little while ago. What we do is, sorry, it's actually on the board still, that capital T, that is always being subtracted off. And that's most of the work that I do, right? So getting the predicted model out by observing these pulsars for each individual time series, that's what is going into the capital T. So that models all of the deterministic effects. Plus, at a final stage, we can even add some non-deterministic effects, but we prefer to do everything in the Bayesian domain now. So all of what we do is we say, instead of just considering the T, I think that's T2, or no, I can't read the notation from here, but the first difference, we include with that in covariance all of the other stochastic noise processes, and then we try to estimate all of them together through. No, there's no assumption on the HIJ. What the thing is, the capital T part, it comes from a number of deterministic effects. And what you can do is you can measure those deterministic effects with incredibly high precision. So you can really measure how fast the pulsar is moving on the sky, or how the rate of rotation is changing over the 10-year span, etc. You can do this with very, very high precision, and you can subtract it off. And then what you do is, in the residual domain, you say there must be an HIJ, that there must be the effect of the gravitational waves. There must be other stochastic noise processes which are covariant with the HIJ, and you can put all of this into the design matrix, and then fit for everything simultaneously using Bayesian techniques. That's how we actually perform the search. So the HIJ, we don't make any assumptions about it when we are calculating the capital T. The point is that you can do the capital T calculation very well without worrying about any of the stochastic effects. So which is why in reality PTAs are a frequentist Bayesian technique, where you do this capital T measurement using very, very standard techniques, subtract it off, and all of the fun stuff is then in the residual domain.
So to give you a theory answer to this, the question you asked,
yeah.
The information of the polarization is like he asked. You have to calculate, you put in your polarization, which is maybe if you have circular polarization or you just have a plane polarized, calculate the predicted correlation, and then you compare with the observation. And for the frequency part, you have only the h as a function of frequency. So in the frequency domain, you have the h. You would take the Fourier transform, you will get h in the time domain. So that way you will predict, you will have the polarization and also the time dependence. You can reconstruct from.
Okay. Thanks.
More questions? Comments?
Okay, so my actual concern is that, so if I want to know the source of this HIJs, so from the PTA data, how can I just reconstruct that? Okay, from this kind of sources, this HIJs.
Yeah, so you have what you have to predict is the spectral SF. Take the source, predict the HT, then take it in the Fourier space, and from that calculate the spectral index, that SF. So SF is represented like F to the power, some power law. And then the observations give you what is SF as a power law, SF as a power law. And you compare the two to see whether your source is the correct source or not, right?
Okay, thanks.
So, are there any more questions? Okay, so in that case, let's thank Professor Mohanty again.
Okay, thank you.
And